All right, in this video we're going to talk about how to assess protein conformational stability using variable temperature circular dichroism. So first we need to talk about what circular dichroism is. And to introduce this topic, I need to remind you of something from organic chemistry, where we learned that chiral molecules rotate plane polarized light. Okay? So what is plane polarized light? It is light where the electrical component of the electromagnetic field is, for each photon, is oscillating in the same plane. So if we were looking at the plane of oscillation for a particular photon, and then another photon after it, and another photon after it, they're all oscillating in the same direction. And you do this by shining light at something called a polarizer. A polarizing lens. And the structure of the polarizing lens absorbs all the light that's not oscillating in a given direction. So you can have non-polarized light, which is oscillating in all sorts of random directions. And once it passes through the polarizer, and I feel like we need to change color here. Once it passes through the polarizer, only the components that of each photon that are oscillating in the plane allowed by the polarizer pass through. Okay? And why is this important? Well, chiral molecules have an interesting effect on plane polarized light. But let's talk about plane polarized light briefly. Here is the plane of polarization. And we're looking down the path of the photon. And this is the electrical component of the EM field. And at any given point, that wave will be oscillating from here to here according to some sine function, wave function, okay? Now, interestingly, you can represent plane polarized light, and maybe I should make it clear what I mean by this. When I show this double-headed arrow as though it's plane polarized light, what I mean is at time point suppose we start out at time 0 and the vector looks like that, and then some amount of time later it looks like this, and some amount of time later it looks like this, and some amount of time after that. And these are arbitrary time units. And if you were to plot this, you would see the familiar sinusoidal function that we associate with light waves. Okay? All right. Now we're going to do just a little bit of vector math. Great. I'm going to argue that you could represent the blue vector at time point 1, which represents the direction and magnitude of the electrical component of the EM field of this particular photon, as two vectors that add together, two vectors, purple and orange, that add together to give us the blue vector. And these vectors are each the same distance or the same angle away from the blue vector. So, oops. So angle 1 and angle 2 are equal to each other. I guess they're equal and opposite to each other. Meaning that we can represent this blue vector 1 as the sum of two vectors, one moving off in the counterclockwise direction and the other in the clockwise direction, and both equally spaced away from this vector. Okay, and then, and I'm sorry, I should have represented these vectors as being about as long as the blue vector but and if you were to add vector math, add the orange vector and the purple vector, doing the appropriate vector math, you would get the blue vector. Okay. Similarly, when we come to time point 2, and the reason that, I'm sorry, the reason that the orange and the purple vectors add up to become the blue vector is because their x components cancel each other out. All right, if horizontal is x and vertical is y. And I know I'm not explaining this really well, and maybe I need another try. At time point 2, the vector in the polarized light has a much lower magnitude, and this, of course, is because you can imagine the full-length purple and orange vectors splayed out like this, and having the same length as before, only their angles with respect to the blue vector are closer to 90, and most of their magnitude is in the x direction, The x component of the orange vector cancels out the x component of the purple vector, and they add together to form a smaller vector. And of course, at time point 3, when the magnitude of the the electrical component of the EM field is 0, you could imagine that you've got the purple and the orange vector present, but they are pointing in opposite directions, and so the overall magnitude of the vector is 0. And so we might continue with purple and orange vectors here. At this point, they would be more in the y direction, and then here, presumably they would both be aligned in the minus y direction. Okay, so we can represent, what I mean to communicate here is we can represent plane polarized light as the vector sum of the purple vector, which is rotating in the clockwise direction, and the orange vector, which is rotating in the counterclockwise direction. The purple vector that is rotating in the clockwise direction, we're going to call right-handed circularly polarized light, because that vector is constantly rotating at each of those time points. And we will call the orange vector left-handed circularly polarized light. Okay, and you can think of plane polarized light as a one-to-one mixture of right-handed circularly polarized light and left-handed circularly polarized light. Of course, right-handed and left-handed are different from each other. They are mirror images of each other, and you might expect chiral molecules to interact with right-handed versus left-handed polarized light in different ways. So if a chiral molecule, for example, once we go through the first polarizer, we've got, going back here, we've got plane polarized light, which we have said is a one-to-one mixture of right-handed circularly polarized light to left-handed circularly polarized light. Now, if we allow that light to pass through a chiral sample, imagine what will happen if the chiral sample absorbs more left-handed polarized light than right-handed polarized light. Suppose that once the sample comes out, it's now, let's say, 75% left-handed or right-handed polarized light, circularly polarized light, and only 25% left-handed circularly polarized light. And if that's what happens, what might you expect to see? Well, if we look down here at how we represented the plane polarized light, where at each step the orange and purple vectors are equal in magnitude but have opposite angles with respect to the original blue vector. Imagine what would happen if at each of these stages we shortened the orange vector because more of it had gotten absorbed. If the magnitude of this vector in the theta 1 direction is half the size of the vector in the theta 2 direction, that's actually going to cause our plane of polarization to rotate. That is, whereas before we had this, after the fact, we might have only this. And in that case, the x and y component, the x components don't totally cancel each other out, and so the vector sum of these two vectors is going to be something like that. In other words, we will observe, and it will look like the plane of polarization has rotated. And it turns out that if we have, and we can analyze that with a detector. Turns out you need another polarizing lens, but that's neither here nor there. Okay, so we've talked about how a chiral sample can absorb more of one-handedness than the other. And this is how chiral samples rotate plane polarized light. Okay? Well, proteins are chiral molecules. And we can actually, let me back up just a bit. If we look at what our new vector is, we can actually measure the angle between what it was originally when it was polarized versus where it is now. We can calculate the angle between those two vectors, and we can measure it in degrees. We call this in organic chemistry alpha, or optical rotation. Now, proteins are chiral molecules, but they also have interesting shapes that themselves are chiral. For example, the alpha helix is right-handed. And when proteins are folded in particular shapes, the angle at which they rotate plane polarized light can be diagnostic of those shapes. So we can do an experiment where we take plane polarized light of all kinds of different wavelengths. We use a monochromator to determine, to make sure that the light we're using is at a specific wavelength. The wavelength will be called lambda according to what we defined it in physics, and it will be generally given in nanometers. And then on this axis we might have angle of rotation. Now, it turns out that this angle of rotation depends on the concentration of the sample. It also depends on the path length, that is, the distance through which you made that light pass, the distance in the sample through which you made that light pass. It's kind of a Beer's law relationship. And then also depends on the number of residues in a protein. Because in this range, in the range of wavelengths that we'll be talking about, which tends to be around 200 to 260 nanometers, this is in the UV, and at this in this wavelength range, it's the amide bond of the peptide backbone that is doing the absorbing of the plane polarized light. So it turns out that instead of taking this angle of rotation directly, we're going to normalize it. So normalized angle of rotation. All right. So what is this normalized angle of rotation? We're actually going to call this molar ellipticity, and we're going to give it a name theta in brackets. And molar ellipticity theta is going to basically be the angle of rotation divided by path length and concentration, and then we're also going to divide it by n, which is the number of residues in the protein. All right, and I want to make sure I get the units all correct. Let me again define these terms. Alpha is the angle of rotation, and this comes in, needs to be in units of degrees. Okay. L is path length and needs to be in units of centimeters. And then C is protein concentration, and this needs to be in units of decimoles. This is weird. Decimoles per centimeter cubed. you can do the conversion of decimals per centimeter cubed into molar, which is moles per liter, right? So decimals per centimeter cubed, there is 1 mole for every 10 decimals, and there is let's see, 1,000 cubic centimeters per liter. So in other words, if I wanted to convert a number x in decimals per liter into molar, yeah. So the conversion factor, between decimals per centimeter cubed and molar is 100. If you want to have x, whatever number in units of decimals per centimeter, and you want to convert that into units of molar, you have to multiply x by 100. All right, sorry about that. That was kind of confusing. And then finally, n is the number of residues in your protein. Okay, so path length for most of our experiments is 1 millimeter, so 0.1 centimeter cubed. Protein concentration depends. It ranges anywhere from 15 to 100 micromolar, and you can do the conversion of that 15 to 100 micromolar into decimals per centimeter cubed. I will tell you that 15 micromolar equals, let's see, 1, 2, 3, 4, 5, 6, 7 equals 1.5 times 10 to the minus 7 decimals per centimeter cubed. Okay. Now the angle, so those are things that we know. The thing that we measure here is the angle of rotation alpha. And our CD instrument gives this to us in millidegrees. And of course, there are 1,000 millidegrees in 1 degree. So to convert a number x in millidegrees into a number in degrees, we would need to divide the millidegrees by 1,000. Okay. And I guess I should be clearer about that. Alpha and millidegrees, we're going to call this just the Greek, angle of rotation in millidegrees, we're going to call the Greek letter delta. So alpha is going to equal delta of your sample minus delta of your blank. You're going to do 2 experiments, one where you measure the angle of rotation of a sample that has your protein in it, and the other with a sample that's identical but lacks the protein. And then we're going to divide that number in millidegrees by 1,000, and that's going to give us the angle of rotation in degrees. So we might say delta S delta B minus delta B over 1,000 times L times C times N. Okay. Now these numbers tend to be in the 1,000 to 30,000 units of degrees. And in the denominator, we have centimeters times decimals per centimeter cubed times residues. Or in other words, degrees centimeters squared per decimal per residue. And these are the units of molar ellipticity. And so because we don't like to plot values on a graph with lots of zeros on them, we're going to actually divide by another factor of 1,000. And that will give us the molar ellipticity in degrees centimeters squared per decimal per residue times 10 to the minus 3. And we'll actually put that on our we'll put those units on our y-axis so that anybody knows when you see 20 on the graph, it actually means 20,000 degrees centimeters squared decimal per residue. All right, that may be more than you wanted to know, and it may be confusing, but that's what we're going to put on this y-axis, the normalized, and that's what we mean by molar ellipticity, or normalized angle of rotation. It's in degrees centimeters squared per decimal per residue times 10 to the minus 3. All right, so we do the CD experiment. We calculate from our observations what this molar ellipticity is. The reason we want to normalize this angle of reflection is so that we can compare different samples and different proteins that were analyzed at different concentrations. And that's what this molar ellipticity gives us. Now, suppose a protein is completely unfolded. Suppose it is a random coil. If that's the case, then we expect the CD spectrum to look something like this. So we'll put 0 here. We'll put something like minus 30 here. 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, and then 20 here. A random coil starts out with a molar ellipticity of about 0 around 260. And then as you start to get closer to 10, 20, 30, 40, 50, as you start to get closer to 215 or so, you'll increase slightly into positive territory. Oops. And then start to go strongly into negative territory by the time you get to around 200 nanometers. Okay. In contrast, a protein that is alpha helical and by random coil we just mean unfolded or disordered. In contrast, a protein that is alpha helical will also start out around 0 molar ellipticity at about 260. But as you start to get closer to about 235, it starts to decrease. And you see a minimum at about 220. And then there tends to be another minimum about 208. And then as you get closer to 200 nanometers, you cross through 0 and start to go into positive territory. And if you're able to, if your instrument allows you to go to lower wavelengths than that, you can sometimes see a maximum. So the minimum wavelength is about 222 nanometers for an alpha helix, and the second one is about 208 nanometers. And sometimes the relative size of these minima can change. For single alpha helices, the minimum at 208 tends to be deeper than the minimum at 222. For alpha helices in helix bundles, they tend to be much more equal to each other. And you'll see values for helical proteins in the -20 to -35 kind of region. Because the CD signal is so sensitive to concentration, we are very careful about interpreting the absolute magnitude of the CD signal. There's a lot of tradition in the literature of using the molar ellipticity of a protein at 222 to calculate the percent helicity, or how helical the protein is. But relative to some standard compounds. However, that calculation is only as good as your standard folded and unfolded compound assumptions are, and in any case, small changes in concentration can lead to large changes in the absolute magnitude of the molar ellipticity at 222 nanometers, and therefore I interpret the molar ellipticity at 222 with caution. But an important point here is that there is a difference between in the CD signal of a folded protein that's alpha helical versus a random coil protein that's unfolded. You can see quite a large difference. We'll illustrate it with a dotted blue line here at 222. Quite a large difference between molar ellipticity values. And that means you can tell whether something's folded or unfolded. All right. One other thing is that we sometimes work with the WW domain. The WW domain tends to have the same ellipticity value at lower wavelengths, and then as you approach the wavelength of 227 nanometers, you start to see a maximum, which then decreases. And so there you'd be looking at this difference to tell how full the WW domain is. I'm not showing the wavelengths at lower values because I can't remember what they tend to be for the WW domain. WW domain is a triple-stranded anti-parallel beta sheet structure. Other beta sheets tend to have maxima in other types of areas. Let's see. So what this means is that the spectrum at a particular wavelength near a maximum, you can tell what the CD signal for a folded protein versus an unfolded protein is. Okay, that's important. Now, how does this apply to two-state folding? All right, remember that for two-state folding, all we have in solution are, for a monomer folding, unfolding situation, all you've got is unfolded state plus the folded state. Okay. For monomer dimer, you've got monomer plus 2 times the dimer concentration. Monomer trimer, you've got monomer plus 3 times the trimer concentration. For monomer tetramer, you've got monomer plus 4 times the tetramer concentration. Okay. We're going to make the assumption that because CD signal is related to concentration, we're going to say that the CD signal for the monomer is going to be equal to the CD signal for the unfolded state plus the CD signal of the folded state, in this case our alpha helix. But it's not going to be the sum, it's going to be the weighted average. That is, the actual CD signal that we observe, the molar ellipticity we observe, is going to depend on how much is folded and how much is not folded. So we're going to put fraction folded here times the signal of the folded state. And then we'll put fraction unfolded here for the signal of the unfolded state. In other words, the overall signal that we see is going to be based on the percentage of the folded state and the percentage of the unfolded state. So if we have 50% folded plus 50% unfolded, it's going to be 0.5 times the CD signal of the folded state plus 0.5 times the CD signal of the unfolded state. We can make this a little simpler because of the two-state folding, if you know the folded fraction, you also know the unfolded fraction. And we can do this for any of the monomer, dimer, monomer, trimer systems that we've talked about so far. That is, oops. We can put monomer there and dimer there, or monomer there and trimer there. By the way, if you're hearing funny sounds, that's Jack downstairs trying to annoy his brother Adam by making a smoker's cough laugh. I don't know where this comes from, but it works 9 times out of 10 to make Adam mad. All right, so during an experiment, when we observe what the molar ellipticity is for any given protein, it's going to be the weighted average of the CD signal for the folded conformation and the CD signal of the unfolded conformation, weighted according to how much is folded and how much is unfolded. And these, the F value in blue is this fraction folded that we calculated previously and showed you how it was related to equilibrium constant and in the case of the dimer, trimer, and tetramer to the total peptide concentration. All right, well, that's good, but if we're dealing with a protein that's 100% folded, we don't really get to see this weighted average of the folded and the unfolded state. And so what we can do is we can change the conditions of the experiment to alter the equilibrium between folded state and unfolded state. For example, we can take a sample. Let's suppose it's an alpha helical sample, so we're looking at 222 nanometers. And this is again in degrees centimeters squared per decimal per residue times 10 to the minus 3. And let's let this be minus 30. This be 20. And we're going to slowly increase the temperature. We can do that in degrees C. This will be 0. This will be 100. And at first, we will see that the molar ellipticity decreases a little bit, but not by a lot. Then we're going to see a time where it changes a lot, and then we'll see a time after that where it also doesn't change very much. In the region where the CD signal doesn't change a lot at the beginning, we're going to call that a folded baseline, and the assumption here is that the protein is 100% folded, and that any change you see in the CD spectrum is just related to the susceptibility of that CD spectrum to temperature or its variability with temperature. For many proteins, this varies linearly, usually with a positive but very small slope. This linear region after the large change, we're going to call the unfolded baseline. And we're going to make the assumption that here the protein is 100% unfolded. And then this is the messy middle, which we're going to make, which we're going to label purple. And in this purple region, we have a mixture of folded and unfolded, where the overall CD signal that we observe is equal to 1 minus F times the concentration is a weighted average of the CD signal of the unfolded state and the CD signal of the folded state. So the CD signal of the unfolded state is usually linear with temperature, and the CD signal of the folded state is usually also linear with temperature. And then in the middle, we can observe a mixture of folded and unfolded states. At each point along this line, we can calculate a fraction folded. And the way we do that conceptually is we will extrapolate a line for the folded conformation and extrapolate a line for the unfolded conformation. And then we will say at any given temperature, we're going to observe the distance between our data point in purple and the folded baseline at that temperature, and then our data point in purple and the unfolded baseline at that temperature. And based on that, we can calculate fraction folded. So fraction folded is going to equal, just call this distance 1 and this distance 2. Fraction folded is going to equal distance 1 divided by distance 2 plus distance 1. In other words, of this space between fully folded and fully unfolded, how much of it have you traversed at this point? At the purple point that I was indicating, you'd predict fraction folded would be something around 25%. Whereas for this point, you might predict that fraction folded would be somewhere around 85% or something like that. All right. So once we have chosen a fully folded baseline and a fully unfolded baseline at each position in the transition region, we can calculate fraction folded. So we can compare the observed fraction folded versus the calculated fraction folded that we get from equilibrium constant and total peptide concentration. And remember, we get equilibrium constant from delta G. And we can compare and alter the values of delta G until we find a calculated fraction folded that matches the observed fraction folded. All right. It doesn't just have to be temperature, it could be denaturant. That's our introduction to using variable temperature CD data to assess conformational stability. We'll call that part 1 because there's still a lot to talk about, but I feel like this is a good place to stop for now. All right, last time we were talking about how during a variable temperature CD experiment, the observed CD signal we get at any temperature is the average of the unfolded CD signal, in red, and the folded CD signal in blue, weighted according to how much of each is present in solution. So at 100% folded, we're going to have a CD signal along this blue line. At 100% unfolded, we'll have a CD signal on this red line. And then once we start to have appreciable amounts of folded and unfolded in solution, we start to be in this purple area. And we're assuming that the CD signal at this point is the average of this value on the folded baseline and this value on the unfolded baseline, weighted by how much of the unfolded protein is in solution versus how much of the unfolded protein is in solution. And this equation here is just a way of representing that relationship. Now we've said in some cases that these folded and unfolded baselines vary linearly with temperature. Sometimes they are just a horizontal line, other times they are a line with a slope. And you have to be prepared for either option, and we'll talk a little bit more about that later. So we're going to call our observed molar ellipticity versus temperature data we're going to represent that with this expression. And we're going to want to use those data to obtain some interesting thermodynamic parameters. So the fitted or predicted molar ellipticity versus temperature data we're going to call theta fit as a function of t. All right. And based on the equation we've described here, we're going to say that the fitted molar ellipticity as a function of temperature is equal to 1 minus the fraction folded times the CD signal of the unfolded state plus fraction folded times the CD signal of the folded state. All right. Now, as I said, we need to take care of the fact that the unfolded CD signal and the folded CD signal vary linearly with temperature. So we'll say that the unfolded CD signal is equal to A plus B times T, where A is the intercept and B is the slope. Similarly, we will say that the CD signal for the folded state is equal to, I think we use here A plus B times T, and here we use C plus D times T, where A is the folded intercept and B is the folded slope. All right, so we can revise our equation for the fitted molar ellipticity. 1 minus F times C plus D times T plus F times A plus B times T. All right, and that we get just by substituting in this definition of how the unfolded CD signal varies linearly with temperature and how the folded CD signal varies linearly with temperature. All right, so that's one way that we've captured some of the temperature dependence of the CD signal that we see as the experiment goes on. But as we will see, fraction folded itself is temperature dependent. And but this expression for the fitted molar ellipticity is true for all, or rather is reasonable for all two-state folders. Okay, now fraction folded is also temperature dependent. And it better be, or else we wouldn't see this sigmoidal behavior where the fraction folded can change as we go from one temperature to another. So, and the expression for fraction folded depends on the stoichiometry or the oligomerization of the folded conformation. And that's what that's what I had been attempting to describe above, or rather in the previous lectures on fitting data. So as an example, we talked about how for a monomer equilibrium, folding and unfolding equilibrium, fraction unfolded is related to just equilibrium constant. For the monomer-dimer equilibrium, we have a slightly more complicated expression for fraction folded. And then as we talked later for the monomer-trimer equilibrium, we were able to obtain this equation from Mathematica. This is a simplified version of what I showed you in that previous lecture about monomer-trimer folding equilibria. This is the expression for fraction folded. Notice that for both the dimer and the trimer equilibria, fraction folded depends only on equilibrium constant and total peptide concentration. Total peptide concentration we know, K we don't know, and we're going to have to predict what K is. In contrast, the monomer depends not on total peptide concentration but only on K. And finally, we found that you can also do this for monomer tetramer equilibria. What I've shown you up top here is an expression for the concentration of the monomer. But that's not quite fraction folded either. To get fraction folded, you would need to take this monomer concentration, take it to the 4th power, multiply by 4K, and divide by P. And you can simplify that, and if you wanted to. I don't recommend doing it by hand. Mathematica is really great. But you actually don't even need to simplify it simply because if you define these two equations in Mathematica, it will do the math for you. Okay? So we've now got fraction folded defined for monomer, dimer, trimer, tetramer. And for dimer, trimer, and tetramer, the fraction folded depends on total peptide concentration and on equilibrium constant. Okay. But equilibrium constant is also temperature dependent. It better be, or else the fraction folded could never change. We've said before that equilibrium constant equals the number E raised to opposite of delta G divided by RT, where R is the gas constant and T is temperature. So that's fairly simple. And if we wanted to, we could substitute in this expression for K everywhere K appears in each of these equations above. We could do that and that would be all right. But we can also just let Mathematica do the substitution for us. And then finally, delta G is also temperature dependent. And again, it better be, or else K would not vary and fraction folded would not change, and we would not see that nice variable temperature CD sigmoidal transition.